Hello, my name is Xinghe. I am a research scientist at the University of Michigan. Today, I'm going to present our paper, Sparse-TPU, Adapting Systolic Arrays for Sparse Matrices. The goal of this paper is to extend the range of TPU-like accelerators to execute the sparse matrix workload efficiently. Because TPU is designed for deep neural networks and can only be used to accelerate dense matrix operations, which limit its application scope. To achieve this goal, we propose to modify TPU-PE with minimal effort. In this paper, we only add simple logics and a few registers in the PE design so that the overall array overhead in floating point implementation is only 12%. With proposed design, STPU achieves significant speed up and energy reduction over TPU when execution sparse matrix vector multiplication. Here is the outline of this talk. First, I will talk about the motivation of adapting systolic array to handle sparse matrices. Then I will show how to use matrix packing to create a regularity so that the sparse matrices can be mapped onto the systolic array efficiently. Then I will show the proposed Sparse-TPU data flow. And to support this data flow, we also propose a modified PE design. In addition, instead of using the naive matrix packing algorithm, we proposed several optimizations which help to improve the density of the packed matrices. Lastly, the evaluation part will prove the effectiveness of proposed scheme. The idea of systolic architecture is not new. It was invented in 1980s. Because of the recent popularity of DNNs, Google, we developed a TPU architecture. The kernel of TPU is actually a 2D systolic array. We show how the systolic array works in the figure on the right-hand side. Assuming the weight is preloaded onto the systolic array, it's actually 1-to-1 matching. So the input X will be sending from the top and streaming down to the bottom. The P's will perform corresponding back operations. So in the first cycle, the X will going down and X0 will be multiplied by W00 and generate the partial sum Y0. And in the second cycle, the X keeps going down and Y0 will be accumulated with the product of W01 times X1. In the meantime, X0 will be multiplied by W10 to generate Y1. This process keeps going and the output will finally be generated through from the east edge of the systolic array. TPU can achieve high performance and throughput because those massive parallel PEs, they work in a synchronized step. Ideally, in each cycle, there will be one output generated. However, this architecture cannot be able to handle irregular operations like sparse matrix operations, because this will lead to significantly underutilized PEs. In this paper, we aim at performing sparse matrix vector multiplications in a highly scalable way through hardware and algorithm co-design. Naively mapping sparse matrix vector multiplication on a systolic array will lead to underutilized PEs. So if we perform the same 1-to-1 mapping, the colored non-zeros will be mapped onto the systolic array. However, the zeros which will also occupy the PE cells, but these zeros will not contribute to the output of the sparse matrix vector multiplication and lead to significantly resource underutilized and also increase the unnecessary idle cycles. So matrix condensing is a natural way to map a sparse matrix onto the systolic array. because the sparse matrix column can be merged together to create a more condensed format. And however, since the matrix tracking is actually an NP-complete problem, researchers leverage the greedy algorithm for column merging. In this case, there will be 3 condensed columns generated as shown in the blocks 1, 2, and 3. This condensed format will be merged into groups. And so each of them will be mapped onto the systolic array and occupies an entire column of the PEs. The modification to this is you need to send multiple input vectors to the same columns instead of 1 to 1 in conventional systolic array. But how to design the interface? In the conventional method, parallel streaming data flow is shown, and the input element group will be sending from the top to the bottom in parallel. It's worth to note that they need to use a parallel buses and a large max to select corresponding atom for the MAC operation. However, this method is not scalable because for the really sparse matrices, it's possible that more than 100 columns will be merged together. So it will have a really large overhead by adding those buses and the large max to perform the selection and the data streaming. Instead of using parallel streaming of the input vectors, we use the sequential processing of vector input as shown in the figure on the right-hand side. The X0, X1 is a streaming group. It will send in the systolic array sequentially. So does X2 and X3. As the animation shows, in each clock, the input stream will propagate one step downwards. So in order to support this scheme, we use sequential streaming. And so it only uses limited number of buses without incurring too much overhead. And also, the streaming of the 2 different groups are overlapped so that the latency can be high to boost the throughput. For example, let's taking a 512 by 512 matrix as an example. We assume the matrix tracking can reduce the number of columns by half. This is usually a conservative estimation because most matrices we handled is really sparse. So in this case, because the matrix is larger than the systolic array, so a common way is to block the sparse matrices. In this case, for the original sparse matrices, 16 blocks will be used. And when it's mapped onto TPU, each block will consume 128 cycles. So given 16 blocks, the total number of cycles is 248 cycles. With the packed matrices, because the number of columns is reduced by half, so there will be only 8 blocks used, and each block will consume 129 cycles because of the overlap. Even though it's overlapped, there will be a minor overhead, and so the total number of cycles is 1,032 cycles for the packed matrices on STPU. So the total execution time got reduced by 50%. And we need to make modest modification to the PEs to support this data flow. Particularly, we made 2 modifications. The first one is instead of using a big max to select the input, we use simple index matching by adding a simple comparator to compare the index of the input X with the index stored weight. And we also support overlapped input by adding one bit end signal to indicate the the last element of the input vector stream. So in this PE design, there are 4 modes to support this data flow. The first one is index mismatch mode. When the input index doesn't match the one stored in the weight, the value of the input x will not be stored. When the index of the input x matches the one stored in the weight entry, the x value will be stored and for later MAC operation. In the mount and accumulate mode, it will be activated when the delay and signal is high. And at this moment, the PE will perform MAC operation with the partial sum from the left PE and perform the MAC operation and send the results to the right neighboring PE. And even though with matrix packing, it's still possible that there are zeros in the condensed matrices. So we add a bypass mode, which always bypasses the partial sums when the PE stores a 0 entry. So far, we are using naive matrix packing. The greedy column packing works on the matrix columns as candidate, and it doesn't allow any collision. We notice that a few collisions in the columns prevent the merging of 2 columns. So if we allow collisions, will this packing algorithm getting better? The result is yes. We propose 2 different optimizations. The first is partition-wise packing. Another one is collision-aware packing. In the first partition-wise packing, the motivation behind it is that when the column length is really high, no matter with these 3 density levels, the probability of collision is higher than 90%, which basically means you can't merge any of the columns. But if you look at the paper, look at the figure, when the column length is small, the probability of collision will reduce significantly. So instead of applying the column merging on the entire column row, entire matrix column, we first slice the sparse matrices into several partitions, and then we apply packing on each partition so that the density can be improved. So the experimental results shows this packing optimization improve the density by almost 14 times compared with the naive packing. Because of a few collided entries prevent the merging of different columns, we proposed a collision-aware packing scheme. It's actually a 2-step process. The first one is relaxed collision packing. And we apply user-selected constraint like how many collisions should allowed per row and how many collisions group in a group. This constraint will perform a trade-off between the packing rate and the collided entries. And this step will generate a set of packed groups. And even after this step, there will still be residues which cannot be merged with the packed groups. So we perform another step. It's a collision-free packing that will generate another set of packed group. These 2 groups will be concatenated together to create the final packing results. Here is the example of how the relaxed collision method, the step 1, works. In the original sparse matrices, from C0 to C5, none of them can be merged together. If we relax the collision constraint, actually you can merge C0, C1 to M0, and C2, C4 to M1, and so on. But there will be collided entries R0, R1, R2. If you apply another round of column merging. These collided entries can be packed onto the M1, M0, M2, which create a more condensed packed matrices. This helps to improve the density of the packed matrices when the original density, the density of the original sparse matrix is high. We set up the experiment as follows. We use a 128 by 128 systolic array architecture. We compiled our proposed STPU with baseline TPU and KMZ TPU design. We estimated the power, performance, and area of the design. First, we use a cycle-accurate C++ model to simulate the behavior at the RTL for faster simulation. And then we perform hardware synthesis with the PE RTL. Then we perform place and route to estimate the area, and then we use prime time to estimate the power. The entire task is performed with 28 nanometer process. This is a pretty standard process for digital design. And also we use a broad set of data sets to evaluate the proposed design. We use 15 synthetic sparse matrices. The size ranges from 500 to 10,000. The density is from 0.001 to 0.3. And we use 13 real-world sparse matrices from the UFL sparse matrix dataset. And we implement two different versions of PEs, a floating point version PE and an integer version PE. We first do the results of different PEs. We estimated the power, performance area, and compared with TPU PEs, we have 112% area overhead. It's slightly higher than the previous KMZ work. When it comes to the floating point implementation, the relative overhead is much smaller. It's only 13% overhead, which means STPU is more suitable for scientific computing, which requires higher numeric precision. To compare with STPU design, in the system level evaluation, we use TPU-like systolic array and KMZ systolic array for comparison. We adopt two different STPU schemes, C0 and C1, both of them with using partition-wise packing, but in C0, no collision is allowed during packing. In C1, we use collision while packing. We will show the difference later in the evaluation part. In the system level evaluation, we first evaluate the density improvement of the packing algorithm over the set of synthetic dataset, as shown in the two figures below. For the ultra-sparse matrices, the density improvement is 140 times, while for the higher density matrices, we can still achieve 5.7 times density improvement, even though when the density is large, it's harder to merge columns. It's also worth to note that C0 scheme fails to deal with high density, as the red box shows. By contrast, C1 can still explore the packing opportunity because of relaxed collision method it used. Then we perform the trade-off analysis. We evaluate the execution time energy on fixed sites 1,000 by 1,000 sparse matrices with different densities. We compare the integer systolic array design with its floating point counterpart, as shown in the left figure and right figure. Generally, the TPU energy remained fixed, and STPU energy increases with increased density. As shown in the figure, STPU outperforms TPU in lower density range. As the density increases, the benefit becomes smaller, and beyond a certain point, TPU consumes lower energy than STPU. This is because the sparse matrix packing doesn't work in high density range, and the overhead of modified PE in STPU consumes more energy. It's worth to note that in floating point implementation, the break-even density level is much higher than in the integer implementation because the relative overhead of the floating point P is much smaller. We also show the speed up and energy consumption on UFL sparse matrix dataset because UFL datasets are usually very sparse with the density smaller than 0.1%. So STPU achieves more than 20 times speed up. In integer implementation, STPU achieves more than 6 times energy reduction. In floating point implementation, a better result can be expected. STPU achieves more than 28 times energy reduction. In addition, we evaluated the bandwidth requirement of TPU and STPU because STPU uses data index for selecting the input element and match it with the index stored. So we need extra data. As shown in the figure, when the density is low, STPU actually saves data bandwidth because of matrix packing reduces the total amount of data needed by 5.5 times. When the density is high, as shown in the red box, STPU uses 55% more bandwidth. There are two workarounds for this issue. First one is to use bfloat16 data format, which have enough precision for most scientific applications. The second workaround is using HBM to provide high data bandwidth, since HBM is a premature technology. Now let's summarize this paper. Packing sparse matrix creates regularity, making it possible to be mapped onto a systolic array efficiently. And we propose STPU, which only makes minimal modification to the PEs so that sequential data flow can be supported efficiently. In addition, we showcased that packing algorithm optimization can improve the scalability to handle sparse matrices of large size and moderate density. That's all for my talk. Thanks for listening.